Okay. Hi everyone. Today I'm gonna walk you through NORA, which is the Northeastern Overseas Resource Advisor. It's a tool that we built to help Northeastern students plan their study abroad courses. So the core idea is simple. Instead of clicking through dozens of tables and spreadsheets, or going through that old websites that Northeastern have, students can have a conversation with NORA, and we're going from a manual search to a guided conversation. Okay, so this is a flowchart of what the students deal with today. So let me start you with the problem. First, if you're a student trying to figure out which courses you can take abroad, this is what you actually do. You go to the Geo transfer credit page, and then you pick a school, and then from there you actually do pick a department, then you read the tables to find the course, right? And then like at the end you'll be like, okay, are you going to search for another course? If yes, then you actually have to go through this process again. And then if no, then it just ends the chat. So the biggest frustration here is there's no way to just ask where can I take a certain class like CS3650. You can't have a back and forth conversation with or anything like that. It's all static, and you can't compare options across countries in one place. It is repetitive and time consuming, and honestly, like the workflow was just not built around questions and what students actually need. So the students end up spending more time on the process, and it actually slows them down because they probably have to remember or manually write things down. So they spend more time on the process than actually planning what they're gonna learn and what they're gonna do. So next slide, we have, so this is what NORA changes. So on the right, you can see a UI of our current UI of what NORA will be, right? So instead of navigating through a drop down, instead of and tables, student gets one chat interface where they ask questions in plain English. And you can type what you're looking for, you can get the answer immediately, and you can refine it with follow up questions, just like a real life conversation. Essentially, it is a very AI powered chatbot. So the way we would like to put it is that NORA turns fragmented lookup process into a guided conversation. It's one interface. There are chat sessions and session logs. Like on top right here, you say new chat, and then you'll have a conversation with it. And then when you leave, it will store it in session memory on the left side. So you can see here, like 418 to 26, new chat is here. As you add more chat, it will just keeps adding. You use natural languages, right? You ask questions like you would to a human advisor, and NORA will be able to respond to you. And then if it doesn't get the right question, just ask it follow up, and it will eventually guide you towards the right question. Yeah, so this UI is what we think is pretty clean. Okay, so here are all the capabilities what students can do with NORA, and what each one means for the student. So you can search for a course by name, right? There's a natural language course lookup. So you ask like which universities offer CS3650, for example, and you get immediate options. You can have multi-turn language conversations, ask follow-up questions like what about Germany, as in like, oh okay, you have all the courses now, and then you can ask it like, oh okay, what about the courses in Germany, and without starting over because it has memory in the context of the chat. Topic-based search, you explored interests like machine learning abroad. Like you can just type, oh I want to learn about machine learning abroad, and it, without giving an exact course number, and it will be able to guide you towards all the courses or list some course abroad related to machine learning. And then there's country browsing, where you can quickly see approved destination countries, and also you have a course detail lookup. So each course details like the credit, the prerequisite, the new path in one place. And of course, like I mentioned before, there is session memory. So it keeps the context during the conversation. So planning feels continuous and it doesn't feel fragmented. Um, all right, so that's like basically kind of a baseline of what NORA can do. And then for next, we would like to show a demo.
A live demo comparing the old system with NORA and show how NORA performs. First, let's take a look at the old system. As you can see on the page, you basically have nothing except institution to start with. And for institution, you need to select from the long list of foreign institutions. Now let me just randomly pick one. And then departments. And then the course numbers. As you may already feel, these cumbersome steps without doubt painfully suppress your enthusiasm about studying abroad. So here comes our NORA to help. This is NORA and it's running locally. And as you can see on the page, NORA supports multiple chat sessions. So if you want to query about different courses, you can do them in different sessions or you can just do them in one. It's up to you. And now I'll start to demonstrate NORA's capability by asking questions the way a student might: countries, universities, topics, and specific course codes. Let's start with this. Let's explore where we can go. We can ask, what countries can I study in? Now, NORA gives you a brief overview of all the option countries. And if you want to know more, just tell NORA, give me more. And next, let's try an exact course match. We can ask, which university in Australia offers something equivalent to CS 3650? When you name a specific NORA system course, NORA looks up the approved equivalencies, partner schools, and their courses. And now it gives you the options. Let's explore them. For each course, you can click this Show Details to view the informations. Let's say this is from the University of Melbourne. And this is from Queensland University of Technology. And for each course, you can show the details so you can take next steps. And now let's going down the same thread and ask about a new place. What about in UK? Oh, there are no approved equivalency for this course in UK. So next, you might want to ask about different country or region. Okay, this example is about the exact course match with the course code. Now let's try a different topic search without course code. We can say, I'm interested in machine learning. What course abroad cover that? NORA is generating the options. So you don't need a course number and you can describe a topic and NORA surfaces relevant abroad options tied to Northeastern coursework. Oh, okay. So beyond that, if you want to learn about a Northeastern course first before looking into the equivalencies, is also allowed. And if you get a course number, you can ask, for example, tell me about CS 4100. NORA first tells you the details, everything we had about this course, and then it also gives you the equivalent courses to select. Okay, After each answer, Nora asks us if we want to narrow down. We can do that. So let's narrow a broad question with a place. Does any university in Europe offer something equivalent? Okay, there are no course in Europe equivalent to this course. Let's ask, what about in Australia? Yeah, we found the equivalent course in Australia. Okay, Nora tells us, see, this course is not directly equivalent to CS 4100, but it covers artificial intelligence topic. So in the future, if you want to take this course, you can apply for equivalence in to the NEU officials. Okay. That's the flow of a student actually uses. Where can I go? Does my course transfer? Follow-ups without starting over? Search by topic? Read about my NORA system classes? And combine topics with plans. Now let's go back to the slides. What you've seen so far is NORA's core functionality, turning a fragmented search into a guided conversation. But our vision for NORA extends much further. We are focusing on our future work on features that integrate deeper intelligence and personalized planning to make NORA truly indispensable. Okay, the future feature one is the equivalency AI engine. First on the roadmap is the equivalency suggestion engine. Right now, NORA works great for pre-approved courses, but imagine you find exciting foreign course that hasn't been mapped to a NORA system equivalent yet. Instead of hitting a dead end, our AI engine will analyze that foreign course description and intelligently suggest the most similar NU course, providing instant AI-powered suggestions. This immediately expands the universe of options for every student. And feature 2 is dynamic data and catalog expansion. To power that intelligence, we need better data management. We plan to implement automated data sync to periodically rescrape the GEO transfer credit site. This ensures our equivalency database is always up to date with new universities, partnerships, and course changes without requiring manual intervention. Crucially, we are also focusing on foreign course catalog expansion. By scraping partner university course pages, we will gather rich, detailed course descriptions, enabling students to search beyond course codes and explore interests using content-based matching. For example, you could ask, show me a course covering the history of Scotland abroad. And NORA will deliver highly relevant results based on course content, not just keywords. Feature 3 is personalized degree planning. The next major evolution is total personalization with personalized planning mode. Students will input their specific degree requirements, their major, minor, and NU path needs. NORA will then leverage the data to build a full semester-long course plan across one or two universities, ensuring every course contributes directly towards graduation. This is supported by our profiles and persistence feature. Allow students to save past searches, bookmark their top universities and course options, and permanently track their major progress within the application. Feature 4 is the enhanced advisor and student tools. And finally, we are enhancing collaboration and decision making. We will implement enhanced advisor tools, providing students with the ability to create a plan, side-by-side course comparison of different options. Maybe comparing a core course option in London against one in Berlin. You can then quickly save and export your shortlist into the standardized format, streamlining the handoff to your academic advisor and turning a typically complex pre-meeting process into a simple click. In conclusion, these future features will fulfill NORA's promise to students, help them spend dramatically less time searching and significantly more time confidently choosing the right global experience. So far, we have fully demonstrated NORA's capability from users' perspective. Now, let's dive into the NORA system architecture.
Hello, I will walk you through four things. First, the overall architecture. Second, what happens in a single chat request, step by step. Third, a deeper look at the four main components, and finally, how we test all of this. The system is pretty standard three-tier setup, but with one twist in the middle. We have an agent doing the orchestration. Let me build this up one layer at a time. At the top, we have the client tier. The student opens our React app in their browser. That's it. No mobile app, no login, just a chat box. When they type a message, it gets sent as a regular HTTP post to our backend. The backend is a fast API service running in a Docker container. Fast API takes the request and hands it to our agent runner. The agent runner is the brain. It's built on the Llama index framework, and under the hood, it's calling uh, OpenAI's GPT-4o mini model. Yes, GPT-4o mini model, not GPT-4. That was a deliberate choice. Mini is fast, cheap, and more than smart enough for our use case. We set the temperature to zero point 0.2, which means the model gives us consistent answers instead of being creative every single time. Now, here's the interesting part. The agent doesn't just answer from memory. It has five tools it can choose from. Think of these like functions the agent can call whenever it needs real data. Three of these tools hit quadrant, which is our vector database. Those are the ones that handle semantic search, like find me courses about machine learning, find me uh, courses like where can I take AI courses or something like that. The others to hit Postgre directly for structured lookups, like show me all the courses that I can take at University of Sydney. The agent reads the student's question, picks the right tool, calls it, gets the data back, and writes a clean answer all in one request. Uh, as on the right side, you can see we have a session memory. That is what makes Nora feel like a real conversation instead of one shot search. We store every turn in Redis. So when the student says, "What about Italy?" after asking about machine learning, the agent remembers that what they were talking about. And at the bottom, the data layer, all three data stores run in Docker containers. Quadrant holds about 31,000 course vectors, each one 384 dimensions. PostgreSQL holds the structured stuff, five tables and two views. Redis holds the session state. And on the far right, we have the ingestion pipeline, but that runs offline, not during a chat. So that's the whole system on one slide, three tiers, one agent, two data stores, and a cache. Uh, Now let me show you what actually happens when a student types a message. So this is a sequence diagram. You read it top to bottom. Time flows downwards. We have six actors: the student, Fast API, agent, Redis, Quadrant, and Postgre. Each one has dashed line going down representing time. So it starts with the student sending a post request to slash API slash chat, just JSON, session ID, and message. Fast API's first job is to load the previous conversation from Redis. If this is turn number 5, we need to remember the first 4 turns so the agent has context. The fast API calls the agent, it passes the new message, the history, and the list of tools available. The agent now has everything it needs. Uh, the agent reads the message, decides which tool to use. This is the smart part. It's not based on if else rules in our code. The model itself figures out, like, is this a direct course code question or a broader topic question or a browse by university question? And this box here, the labeled alt, shows the 3 possible paths. If it's a specific course code like CS3650 abroad, the agent calls quadrant with an exact match filter first. So that's deterministic, no ambiguity. If the exact match fails, it falls back to vector search. Next, if it's a topic question like I want to study machine learning, the agent does a pure vector search with a similarity threshold. Here for our system, anything below 0.35 gets dropped as noise. And if it's browse query like what's available at University of Queensland, the agent goes straight to Postgre with a structured SQL query. So whatever path it took, the agent formats the answer, sends it back to the fast API. Fast API then saves this turn back to Redis using Lua script, which keeps it atomic. So two simultaneous requests can't corrupt the session. And finally, the answer goes back to the student as markdown with clickable links. One request, one response, but the path through the middle is chosen by the model, not by us. Now, let me give you like 4 minutes on the 4 most important pieces. First, agent and tools. We chose function calling over the older React pattern. React worked by the model writing out its reasoning in text. And we have to parse that text. It's fragile. Function calling uses the native OpenAI API, which gives us a clean JSON object back, much more reliable. For each tool, we wrote a very clear description to when to use it and when not to use it. That helps the model pick correctly. Second, retrieval. We use the all mini LM model for embeddings. It's small, 384 dimensions, but surprisingly good for our domain. We also handle something boring but important, like course code formatting. Student unknowingly can type the course code in any format, but our regular expression normalizes all into the same thing before we search. Third is session memory. This is Redis backed with a 24-hour expiry. The tricky part is that if a student sends 2 messages at the same time, we can't have the history get out of order. So we wrote a small Lua script that does the read, append, and write as one atomic Redis operation. And once conversation gets long, like past 6 turn, we automatically summarizes the older messages. This keeps the context window small without losing what matters. And the last ingestion, the embedding isn't just the course title. We build a composite text that puts the foreign course description first, then adds the NU equivalent, That way, embedding captures what the student will actually learn abroad, not just what it's called at Northeastern. Every record goes through a pydantic schema before it lands in quadrant, so we never silently ingest a broken row. So the last one, this is how we keep the system honest. We have 225 plus test functions spread across 19 test files covering 19 different areas of the system. Let me walk you through why each area exists. So retrieval routing is 30 tests. This is the most complex logic in the system. Every tier, every fallback path needs coverage. Payload payload contracts is 60 tests. These are the schema gates. If a bad record sneaks into quadrant, search results quietly gets worse and nobody notices for weeks. These test catch that at ingestion time. Next is the idempotent IDs, is 15 tests. We generate each vector's ID from the course code and university name deterministically. That means if we re-ingest, we don't get duplicates. So these tests prove that. API and endpoints is 45 tests, response shapes, error codes, session reuse, anything that front end depends on. The chat context is 9 test, multi-run memory, filter, carry forward. The thing that makes NORA feel conversational, embedding pipeline is 16 tests, composite text building, model loading, dimension validation, then config and scraper is 17 tests, the scrapers that pulls course data and the settings that configure everything. So the big idea here is that most of our tests are integration style. They hit the real retrieval logic, not mocks. Because if we only tested mocks, silent degradation would have a place to hide. So that's the technical side, three-tier system, and an agent that picks its own tools, proper separation between semantic and structured data, and enough tests to sleep at night.
So the last part is the team reflection and the deliverable artifacts. I will cover what was difficult first. So the first is the uneven workload across sprints and squads. So data scraping was largely done by sprint 0 and middle sprint 1. We realized that the semantic search quality required foreign university course data. The scope expanded significantly and unexpectedly. Embedding squad finished core work within 2 weeks, and after that, no clear embedding work remained. And the agent workflow had major structural issues surfaced at the Spring 1 review, triggered a large unplanned refactor. And I think we think like it ha happens because unlike the project where team can agree on interfaces early and work fully in parallel, our system bottlenecks were data dependent and hard to predict upfront. We had limited prior experience with LM agent system, many failure modes, for example, the brittle rule-based routing and the context window management only became visible once we built and tested, and the gap between what we planned and what the system actually need was wider than expected at each sprint boundary. And also the text management across whole team was a little bit difficult to manage. Since not a lot of members has experience LM and agents, and at first we plan to like everybody work closely on the project, but it gives like much burden on the teams. So with the project going on, we decided like we assign we organize the tickets first, and if anybody willing to work on certain tickets, they will just keep working on it. So I, as a product manager, I give more freedom to my teammates to work on the parts they would like to work on. And then I want to cover what went well. So the first is the team collaboration across multiple squads. Since the data scraping and embedding and the agent workflow, it all works very closely. And there's so many things happening inside of the project. Like the different squads were able to work together to figure out the solution. And also, at the very beginning of the project, we had a very detailed, comprehensive design, and that really helps us to deal with the unexpected problems which came in the middle of the project. And also, the team flexible and adaptability. We started within three squads, the data scraping, embedding, the test scraping has four people, the embedding has three people, and the full stack agent has two people. As project evolved, workload shifted dramatically between squads. Teammates adapted without friction. For example, when Sahel volunteered to take on the entire foreign university scripting efforts across 25 universities, the team relied a ground that without any top-down mandate. And also faced with the choice of building a sophisticated scraping agent vs manually handling each university site, we chose we chose the simple version, like one teammate owned the scraping end to end, and that unblocks the rest of the team and kept the project moving. And it's kind of like the dirty work, and I want to shout out to Sahil who works on that. So the next part is the deliverable artifacts. So for the data, we have PostgreSQL database, Codron vector store, and the raw script data. It covers the GO course equivalency mappings. We have more than 32,000 equivalency data and the full EU undergraduate course catalog and 25 partner university course records with multi-strategy scraper and parser file in our GitHub. And also for the full stack and agent, we have the React Chat UI with session community, starter prompts, and loading state and error handling. And for the backend, we have fast API with full REST um, API like API chat, API query, course, equivalency, export endpoints. And also we have function calling agent with 6 tools. Those are extensible by adding new tool definitions to make NORA more smarter.